Right, okay, so I think that when I made my first video, I said that I was planning on making videos in order of AP Physics units, and then after that I would bounce around to whatever topics I liked or found interesting or whatever. I promptly didn't do that. The last video I made was on projectile motion, I think, and now I'm going to talk about special relativity, so this is not exactly AP order. Oh well. Okay, so anyways. Special relativity only applies to inertial frames of reference, which basically means that it applies to frames of reference that aren't accelerating. So anything that's keeping the same velocity would apply. So whether that velocity is zero, so it's not moving, or big, fast velocity, whatever, as long as it's maintaining that, as long as it's staying not moving, or staying big, fast, same big, fast, that is fine. Velocity not changing. So there are two postulates to special relativity, and the second one has to do with the speed of light. I forget the exact wording of it, but the gist of it is that light moves at the same speed regardless of how fast the thing emitting it is going. So in empty space, light is always going to be traveling with some definite velocity, which people define generally as like a little c. And that's 3 times 10 to the 8th meters per second, which is irrelevant and will not come up again. Goodbye. Okay, anyways, moving on. So let's say there's this guy, and this is like a bird's eye view of his head, and he's in a car, and that car is going along at half the speed of light. So again, that c is just denoting speed of light, and then half that, 0.5. Okay, and so let's also say that he has a friend right here who's remaining stationary. Okay, so he's moving forward at half the speed of light. His friend here is staying stationary while she watches him move forward. So this is a flashlight, and that's a mirror. If he were to shine this flashlight at the mirror, according to his frame of reference, the light's going to go to the mirror and then bounce back to him, which, makes sense. I think that anybody can imagine shining a flashlight at a mirror or some other reflective surface. The light's going to hit it and then reflect off of it back to you. So according to him, the light is going forward and then traveling backward to him, like that. Now, according to her, it's going to be a little different, though, because while it's still going to go forward and then bounce back, it's also traveling forward. So since he's shining the flashlight at the same time he moves past the girl, the path that the light takes, according to her, is going to be something, like this. If it's going to go forward diagonally and then bounce back and then go like that. And all of these different cars represent different points in time. So all of these are just different like snapshots as he moves forward. Okay, and you can see that represented here by the arrows. It's still going to go forward and then hit the mirror and then bounce back to him. But since her stationary point of reference is stationary, it's not moving, the light also had to travel forward relative to her. So it's going forward and back that way, and also traveling in that direction. Now we know from the second postulate of special relativity that the speed of light isn't what's changing here. The speed of light has to be the same from any perspective. However, the distance it travels from the girl's perspective or the boy's perspective is different. So velocity is equal to distance divided by time, and velocity times time is going to equal distance. And we know that the velocity, the speed of light, is staying the same for both of them. So since the speed is staying the same and the distance is changing, that means that the relative time for the girl and the guy is also different. Since her time is going to be longer, it appears to her as though time is slowed down for the guy. Basically, time moves slower for things that are moving. And the faster something is going, the closer something is going to the speed of light, the slower time is going to pass for that thing relative to a stationary point of reference. Okay, so that's basically all there is to time dilation. I'm going to cover length contraction next, which is like the next kind of conclusion of all of this. Anyways, bye.